Good to be back again with Glenn for part two of looking at math, logic, and computation, physical computation especially. And Glenn was going to talk today about math, logic, and the theory of computation, and maybe look at some of the history of it, particularly starting with Frege. So why don't you get us started, Glenn?
Okay. Well, we sort of left off the last talk with talking about the abacus and the creation of what we call the decimal number system now. And that was what happened was we now had a symbolic representation of what the abacus actually did, or the counting board. And then somewhere the stroke of genius happened. People realized that if they just manipulated the symbols that represent the numbers, they could skip all the physical manipulations and just do everything symbolically. We've sort of been on that track ever since. And I feel that that was a good spot. Physical computation used to be taken for granted. That was the physical manipulation to do math. Now, all of a sudden, you could do it symbolically without any reference to physical manipulatives. And so that was sort of the pattern that we've gone on since then, is discovering that once you create these symbols, symbolic systems that you can manipulate, all of a sudden you can do all sorts of crazy things and come up with all sorts of amazing results just by manipulating symbols without actually having to do any physical work. And so we come fast forward to the future. I'm sure all your listeners have run across Eugene Wigner's The Unreasonable Effectiveness of Math.
Mm-hmm.
And that question that the physicists were posing is, why is it that math is so good at predicting physics? You know, you would think that it's just untethered discipline to reality, but yet mathematicians, but people should turn that question around, I'm suggesting, and say, maybe math is so effective because math is a reflection of physical reality to start with. I've not heard mathematicians actually put it that way. I suspect that a lot of developments in math actually began in reference to some physical, experience. You created a symbolic representation for that with rules and grammar, and then that turns into a game in itself, discovering what you can do with symbolically. And then amazingly, things keep coming back from the world of math to physics and make sense. That's a thought. And then the
Well,
next thing,
what that brings up for me is I was listening to a lecture by Arthur Holmes on Aristotle's Four Causes last week. And one of the things he said was that there was a debate between Pythagoras's followers and Plato's followers, or Plato himself. So Pythagoras's followers said that substance imitates numbers, but Plato said that substance participates in numbers. And that makes me think about what you're saying about math being a reflection of physical reality. It sounds like Plato was definitely saying that physical reality participates in mathematics or participates in numbers.
Yeah, so these are actually old arguments. So I head off a little. Aristotle, my impression was he would be in the camp that the symbolic representations are what's real, and that physical experiment is just mimicking or trying to mimic what the true nature of things were, which fast forwards to, would be a whole topic. Galileo's beef was never with the Catholic Church, despite the history you've probably been given. His arguments were against Aristotle and the stranglehold Aristotelian thinking had on what you would call natural philosophy or physics and astronomy now. So you might say Galilean thinking or epistemology, notion of truth is what is true is what is observed, what is experimental, what you can touch. Whereas Aristotelian view of truth is what you could argument, logically present, um, rational debate. And so we're still having basically that same argument today. Um, Apparently, the church had drawn in a lot of Aristotelian thinking into its theology at the time, which was one of the problems. But I've noted that some of the philosophy professors at his university were the first ones historically to bring up the religious arguments. So there's a little professional uh, uh, jealousy going on. But anyway,
Well, so back to Wigner.
yeah,
You're saying
Wigner.
that Wigner talked about the unreasonable effectiveness of math, and some see math as a reflection of physical reality. You said that physical experiment is the mimic, symbolic manipulation was the real. That was
Well, I think that would be Aristotle.
that was Aristotle's argument. Okay.
Not his argument, but that's how I would condense it or reword it in today's language.
Okay. So
Yeah.
where do we go from here?
So I'm just trying to know the debate I sense in like X Twitter. There's people who think computation is the theory of computation with set theory, math logic. That is the true definition of computation. And then there's a subset of heretical group that I'm part of that says no, the physics comes first, and the symbolic representations are secondary. I'm not going to die on that hill. I just want to put it out there to pull this apart so that your listeners know that there are two schools of thought going on. And so if you hear people debate, it's always good to go kind of do a check to say, okay, what is their standard for what is true? Which side of the debate are they coming from? And just leaving it that, this is going to be scattered because I want to touch a bunch of bases. I wanted to come back now. Why does the theory of computation, the mathematical textbooks theory, look like the way it does in the first place? And I would go back to the observation that in mathematics, one of the strongest tools that you can bring to bear on a problem is if you can map a problem from one space into an area in mathematics in another space, and now you inherit all the tools for working on that problem. So
is that like what Maxwell did when he was trying to understand electricity and magnetism, and then he shifted his mathematical framework over into calculus?
Well, James Clerk Maxwell, his area of expertise was hydrodynamics, equations of fluid flow. And he was looking at what was coming out of the study of electricity and magnetism and seeing these equations. And he realized, oh, that looks a lot like hydrodynamics. If I just add one more thing to what the physicists were doing, then all of it collapses down. And I think it was the notion of a displacement current was a little bit extra. And all of a sudden now electromagnetism could be captured in the same mathematical formalism that they were using for hydrodynamics, fluid flow. And then now the rest is history. So there's an example where the math gave you a clue to something that was missing on the physical side. And then once the physicists filled that in, then now the math lined up. So that's one of the reasons I think we have this prejudice that math might be more fundamental than the physics. because often symbolic manipulation gives us clues to missing things to go look for in the physical world. So now getting back to Alonzo Church, this is really scattered, and I'm just going to lay some breadcrumbs and hopefully that people will be tempted to go study the history. As far as I can tell, his area of interest was studying algorithms and how algorithms could be worked on. And it was a natural thing for him to model algorithms in terms of language models, which were very strong. We'll get to Frege. Alan Turing, about the same time, had imagined this system he called what we call a Turing engine now. And it's not really a computer, but what it does is it's a recipe for turning a problem in algorithms into a problem in set theory. So we have two cases where the study of algorithms was modeled into language models, which then we got lambda calculus, or to set theory via the Turing machine. So now that's one of the reasons why if you open a textbook in theory of computation, you'll see a lot of language references and a lot of set theory references. I'm not saying that, though, for me as a physicist, I step back at this point. Okay, what does it mean to say an algorithm? Well, that's where I keep coming back, a sequence of choices defined by a set of rules. And so people have accused me of inventing my own definition of computation, but that's where it comes from, because that was originally what Church and Turing were trying to look at. I think Turing knew Church was doing that at Princeton. That's why Turing came and did his PhD at Princeton. And eventually they worked together and they proved that their two approaches were equivalent. Now, this is a sideline. A Turing machine only encapsulates one algorithm. So what they're saying is every algorithm can be mapped to some Turing machine or Turing engine. That's, I think, the Church Turing thesis. So, but just mapping an algorithm to a Turing engine is not much use. So Turing came up with this, an additional concept, a universal Turing machine. And it's a Turing machine that can emulate any other Turing machine. So if you present it, the universal Turing machine with a program, you have a header file, hello programmers out there, that tells the universal Turing machine what program to load so that it emulates a specific Turing machine. It's a very complicated process that you would never do in practice, but it does allow you to go from algorithms as abstract processes to set theory, logic. Now you have all the tools for mathematics to study what you can't do, natures of problems, and then the forever game of showing things that are Turing complete. One of my people who replied to me on Twitter made the comment that you could turn that into a game, cataloging everything that's been shown to be Turing complete. Like I say, including 2D origami, certain card games, cellular automata. I don't know. It's been fun. I think someone showed that blockchain technology is Turing complete. So they're trying to embed AI into the blockchain framework. So, but before Church and Turing did their work with algorithms, the focus with math logic and set theory was understanding proofs, which again, it's different than algorithms. It's subtle, but it's important. So before Church and Turing, which is probably the 1930s, there were people studying languages and how you could use language to model logic systems. So that's where the tag email post, the tag system, where you see these string replacement schemes for generating new text strings, which sort of sounds like what the language models are doing, generative, where you take a string of words and based on a set of rules, which in this case are a statistical model or neural network, you add to that chain and you keep going and produce more statements. Now, the reason why that was important is you get back to Frege and his notion of logic, math logic as a language system. Now, at this point, if someone's curious, I would simply go and grok timeline for math logic and set theory. And it'll give you a chain from Boole up through all the mathematicians, which there's maybe a dozen main ones. And then over grad students and minor mathematicians, it was a major work, a lot of different directions. So there was this whole edifice built up before Church and Turing ever started what we call theory of computation. And what I found interesting was that of all these people involved, all were mathematicians primarily, except for Frege, who was a linguist. And he was looking at language, and it was out of that math logic as first order predicate calculus, all the stuff that we normally associate with math logic, started out as an exploration of language and how you can construct logical languages. And I thought I was going to have a nice quick history talk, and then I fell into Frege, and it was like, that's a rabbit hole you don't want to go down unless you have a lot of time. But I would encourage people nowadays, if you're interested in language models, to really go back and take a look at Frege and try and understand what he was doing back in the late 19th century that made him come to math logic. And so this is a little tangent. If you're familiar with Thomas Kuhn in his book, I think it was Structure of Scientific Revolutions, which is a major work in philosophy of science. He talks about this phenomena that now if you study music, or you study art, you'll be introduced to the history, different instruments, cultures, how music theory develops and how it reflects the culture. But if you take physics or math class, you don't get that. You'll get a couple hints about history and some of the main players, but no one ever introduces you to where ideas come from in the first place. So I was sort of exposed to that in depth when I got into entropy. We all would automatically think of entropy as statistical mechanics, thanks to Boltzmann distribution. But 10 years or so, I think, before Boltzmann did his work on statistical mechanics, I think it was Clausius, sorry, I'm pulling from my memory vault, had already coined the term entropy. So people, a generation before Boltzmann had already realized that there was something out there and had given it a name. But we don't ever go back and look at that and say, well, what were you guys looking at that you actually were motivated to give it a name? And then you look at it, another Schrodinger's equation. Now that's something out of the blue. If you think about it, you take your physics classes and you learn how to grind it in, 10,000 different ways. But what was Schrodinger looking at to start with that would motivate him to come up with Schrodinger's equation? That is a good question. I have never gotten an answer for. So if you want to understand language models, it might be good to go back and understand or try and see what Frege was looking at that made him go down that rabbit hole in the start. We've sort of lost that. And I'm curious. I haven't seen anyone do it, and if I have times, in this life yet, it would be fun to look at it. I think he was looking at stuff, and I think it was important for us to go back, and I'll suggest later on what I suspect he was doing. Um,
Well,
so
could I ask a
yeah,
definition question about Frege? You said he was looking at first order predicate logic.
well, that's one of the things he coined.
Well, what is that exactly?
Statements, statement calculus, truth functions, truth tables, normal forms. Um, this is a copy of a second edition of my book that I had back in 40 years ago now. I took a course, upper division in math logic, and we started with the very grunt Aristotle, Greeks, they were familiar with logic. We didn't invent logic. It goes, but
But they were using,
what
Aristotle was using syllogistic logic.
syllogistic, what Frege did was actually put it on a formal footing with the language and syntax and grammar. And now all of a sudden you could approach it as how I was saying, if you have a language and you have a grammar, which is a rules to how the language forms, then the grammar you can now study because it tells you what you can do with the language. So you can mathematically grasp the rules and use that to make theorems about what the language can say. That's what Gödel eventually did.
Yeah, I was going to say, so he was laying the groundwork for Gödel.
Yeah, so I don't know if I could share this page. I'll try that. Hopefully this comes up. Can you see that?
Glenn has started screen sharing. That's okay. Now I see
Okay,
a
so when
chart.
Frege was doing his work, this is what has me curious. He did a lot of work in linguistics and the structure of sentence and language and meaning, and he was he was pulling out the logic structures, and his relation looks a lot like sentence diagramming that we had to do back in grade school and middle school.
Yes.
And I don't think kids today have to do that, but I remember diagramming lots of sentences. And as soon as I saw this, I thought, oh my, that's what Frege is doing. He's deconstructing a sentence, and he's formalizing it into kind of like this notational symbols that now he can actually write formulas and text using this notation to analyze the structure of what's in a sentence. So I'll close the sharing now because I think that's enough. And then I got to thinking, yeah, that's when I do FPGA design. The electronics systems are silicon, but I'm typing code. I actually type source code that describes what the silicon is going to be and translates it. So yeah, there's this again, I keep running into this association between language and structure, formal structures of language, and stuff in the physical realm. And it doesn't have to be computation, like it could be games, it could be checkers, all sorts of things. Keeps coming back. There's this constant play between language and physical structures. So I hopefully I'll try and put this into my own words. This is how I explain to myself. What Frege was working on was this notion that if you have a language with some axioms and you have a set of rules, that every sentence that you could write, if it's grammatically correct, then it's logically correct. So a set of grammatical rules automatically generate only true statements. So this is where we get into the
That
notion
doesn't
of,
seem possible.
well, that's what inspired everybody. It's like, whoa, we could take this structure, this language approach to math. And if we know we have a good grammar, then we know everything that can be constructed or expressed in this language will be true as well. So somewhere in here you get, Bertrand Russell and Whitehead's Principia Mathematica, where they were going to generate all of mathematics starting from basic axioms, proof, theorem, lemma. And this is what Gödel's talking about when we talk about completeness or incompleteness. This is a reference to the language model that came out of Frege. This thinking that if I have a good grammar and I have proper axioms, then I can create this machine, language model that will just generative model that will keep spitting out theorems. And I know that they will all be true statements. And if I let the machine keep going, it will eventually output every true statement possible. Okay, this is what, back 100 years ago, this is where the world of math was at.
So this is before Hilbert.
Oh, this is contemporary. Hilbert was part of the mix.
Okay.
So, yeah, I can't go, but that's where the suggestions, the decision problem, I think. He was familiar with the work that Frege and the logician people were doing. And so he was suggesting a project. Can we have a project that could decide if a theorem is true or false? Okay, my memory's fuzzy on this point, so comment section, correct me if I'm wrong, but Hilbert was in this mix along with all these other mathematicians talking about, is it possible now to prove all of mathematics? Is it possible to show that a mathematical statement is true or false just based on the grammatical construction of it without actually having to solve problems? It was exciting times, I think, for mathematicians because they thought maybe we have it all now. Math is done. And then Gödel came along and said no. But we know about Gödel's incompleteness, but Gödel also did completeness theorems as well. And one of the ones he showed was that first order logic, which came out of Frege, and that's basically math logic that doesn't include number theory. So quantifiers, if, else, then, for all, there exist, those kind of operators. Every statement you can make, if it's grammatically correct, will be logically true. And every true statement can be expressed as a grammatically correct statement. But more importantly, every statement which is not grammatically correct is false. And false statements exhaust the possible bad grammatical statements. So completeness means that the language is complete in the sense that everything that is true can be reached and everything that can't reach is false. And everything's decided now. There's no mystery. What Gödel did was, if you add number theory to, or sufficient axioms now to have number theory within your axiomatic system, it's possible within the language itself to create a statement that is not constructible within the grammatical rules of the system. I'm fumbling it right now.
But I mean, is that his famous sentence?
No, I'm not going to try and quote it. No. It was a 1/4 math logic course that started with the basics and ended with a sketch through Gödel's proof. So I've been there once 40 years ago, and I'm not going to try and do it again.
Oh, yeah. I mean, I watched a video on how that all went down, and it's not easy to grasp even.
But once number theory is part of your axiomatic logic language model, you can say, now you can step back and use number theory, theorems from, to prove theorems about what is constructible and what isn't. And so here's again, one of those places where you can take a problem in one area of math and map it onto another. So he took a problem in math logic and language building, mapped it onto number theory, and then used proofs, theorems from number theory to prove what you can or can't do in the logical system of language. So I'm sorry I butchered it, but hopefully I left enough clues for people interested. They can go on. So here we are, back to, theory of computation is part of this vast edifice of mathematics, symbolic manipulation, reasoning. And then there's still come back to the world of, well, an algorithm is just a sequence of choices defined by a set of rules. But what does that look like in the real physical world? Oh, let's see, there's another thing I thought of, that game theory borrows a lot from theory of computation. So if you dive into game theory, it looks a lot like theory of computation. You'll see this pattern if you look at math, that one subject looks like another one from. So, okay, I need to take a break. Do you have
Yeah.
any questions?
Well, I do, because there's so many things missing in my framework of understanding. I guess I'm especially interested in this word predicate. So you said Frege's thing was first order predicate logic.
Okay, I'm going to have to go back.
What does that word predicate have to do with that? Because I mean, there's different
I think a
ways of thinking
predicate,
about predicate. You can just think about it grammatically, or you can think about it as a verb, that one thing predicates another thing. And
it's got a, okay, bear with me for a moment. I have to look it up because I want to make sure I get it correct.
yeah, take all the time you need.
But I wanted to touch on one last thing, that um, a predicate, I think it's a function that takes a statement to a truth value, true or false. Socrates, oh, okay.
Well, I mean, we use predicate in a certain way grammatically as to speak about the Sally threw the ball. Sally is the subject, and
Yeah,
the ball is the
yeah.
predicate.
There's the language on, and then there's a strict mathematical
Yeah.
statement, which
So
I'm not going to spend more time on trying to dig through the book. But yeah,
it's a strict mathematical
yeah,
logic word.
you're mapping statements in language onto Boolean true false, yes, no, 1, 0.
Oh, okay, okay.
So, and
Well,
now
that
you can
helps a lot.
yeah.
That helps a lot.
So the predicate in a sentence is what you're referring. That's the object. Your background is linguistics, isn't it?
Yes, yes. Although, like you, it was a long time ago. I got my graduate degree in 85, so that's what 40 years ago now. And
Yeah,
my linguistics degree had an emphasis in speaking English as a second language. So
yeah.
a lot of the efforts were looking at a pedagogical analysis of English language in order to understand how to help foreign learners understand all the peculiarities of English, because English is a very peculiar language. And then we did do obviously some linguistic studies as well, but we didn't dig into this level of like the logic things in our linguistic studies. I'm
So
sure nowadays they do, because it all ties in with computation and all that. But back 40 years ago, that was just like the very first Macintosh came out, I think.
so to finish up that last sequence, and little historical note is that it is something that fascinates me, that at the beginning of World War II, math, logic, computation was the realm of pure mathematics. So Alan Turing came on, we all know his story with Bletchley Park and helping decode the Enigma machine. There's a whole story there. But by the end of the war, there, the technicians, the electronic technicians and the electronic engineers had taken over computation. So he started out the war, Alan Turing is literally God's gift to humanity, and he ended up the war 6 years later, as someone who was no longer part of the discipline. Computers, the first tube-based computational computers like we would recognize today were produced at that time. The technicians who soldered and maintained stuff, troubleshoot stuff, the engineers who built it, they all came to the forefront. And so by the end of the war, computation was no longer the realm of the pure mathematician. It had become an engineering subject. And the engineers now forever after dominated. But there again, that's why I would encourage people to look at history, to go back to see what it was before then. It was a different world. And the other funny thing is that back in the days when calculators were people, women were the calculators. That was women's work. So along with Alan Turing and his staff, there was a small army of women who did all the handwork to finish a lot of the deciphering. My mom, turns out, looking back, my mom was a calculator back in those days. So that when the first couple of years of computers after World War II, women became programmers. They were the calculators that became the programmers. So there's a funny quote about von Neumann not wanting to waste computer time running an assembler because he considered programming women's work. So anyway, things.
Well, yeah, that's super interesting. I mean, that's
Yeah,
the story of that movie, Hidden Figures. If anybody has not seen it, it's a very
yeah,
interesting movie. Um, Somehow, the main thing that pops out to me about that movie is the fact that they didn't have any restrooms in the building where one of the particular calculators was. So she'd often have to be gone for half an hour to go to another building and find a restroom. So
yeah. So my mother was they were called comptometer operators. And so it was essentially a human Excel spreadsheet. And so anyway, those days are gone. It's all computerized now.
yeah. So now the machine has taken over. So we went from the abacus at the beginning here. We're talking about the abacus and the counting table as being physical computation. Then once the zero came into play and we had decimals, then we had numbers that we could manipulate symbolically and even in your head. So you don't need an abacus or a counting table anymore. But then we come full circle back around to where, like in the early part of the 20th century, they maybe even earlier than that, they started building calculators that you could input the numbers into and it would do manipulations. And is that a kind of physical computation as well?
Yeah, you could say that a computer is a base 2 version of the abacus, which was a base 10 system. So now we have electronic devices that manipulate packets of electrons that zip around or cascade through the structure, the silicon structure. Like I tried to bring out the last time, is that you can look at a silicon chip as this lattice of pathways and junctions and gates where clumps of charge float around very, very fast. And that is I can imagine that's just like beads on the old abacus. It's just multiplied by, several million in complexity and speed. But you're
So,
still
so
manipulating something.
you spent some time designing FPGA.
Yeah, so I do
So as I
FPGA. I don't
recall from my husband, that's field programmable gate array. Is
gate
that right?
arrays, right?
Okay, so does that mean that it's that is not like carved in stone, that it is that if you have an FPGA, it can be altered?
Yes.
Okay.
So you get into very large scale integration VLSI design. There's the ASIC where you actually design the silicon itself, and then it becomes a one-use chip. But then they have what they call field programmable gate arrays, where they tile it with a bunch of little logic blocks, which have little gates and little memory. And then you can have thousands of these little logic blocks all on this silicon wafer. And you can go in and program them using software. So I can turn a logic gate into an AND gate with a flip-flop, or I can make a piece of memory block. And so you can sort of customize your silicon in a sense.
So that
I'm not
seems
sure,
even
but
more closely tied to a physical computation than a regular silicon chip.
it could be. I wouldn't say yes or no on that one.
Okay. Well, I mean, it's
Everything I
probably
do on an FPGA can be turned into an ASIC.
okay.
And a lot of development sometimes goes that way. They will develop a chip
And
as a
ASIC
field
is
programmable gate array in specific
application specific
integrated circuit.
integrated circuit. Yeah.
So if you get the FPGA and your client's happy, and you've got a market of 100,000, you get million of these potential market, then you go turn it into an ASIC part application, which then cuts the cost by a factor of 10, and you make a bazillion of these things, and you sell them and you make money. But if you're only going to make 1,000 or something, then you just stay at the FPGA part level. And they have some impressive FPGA parts out there now that have over 1,000 pins on them. So you can imagine the printed circuit board artwork for something like that gets
Yeah.
very impressive.
Wow. So this brought us up to oh, you were looking something up when we took a break. You were
Oh,
looking
I was looking for the definition of predicate.
Oh, okay. Well, we're not going to worry about that.
And yeah,
As
and
I
my memory
understand now,
was
you said it's a way of mapping a statement onto Boolean logic so that it can be
right.
stated in zeros or ones.
Yeah, there's definitely a very mathematical definition for the term predicate, and I don't
So
want to get it
I
wrong.
have to just throw this in here. I've been thinking for a long time about this whole thing about mapping things onto zeros and ones and how it seems like really, and I'm not at all saying that this is a simulation, and I'm not even close to that. I'm just saying that when you really start thinking about things, they simplify and simplify and simplify. And you can get everything simplified down almost to the point where everything does become a zero or not that each thing is its own zero or one, but that all things start to simplify down into zero or one. And I mean, like for example, this morning I was reading in the Minor Prophets. So I was reading Nahum and Micah and Haggai. And the word judgment is just used over and over and over again. And of course, in our minds, when we think judgment, we think condemnation, we think lightning bolts from heaven, we think earthquakes and all of that. And there is a lot of that kind of language in those Minor Prophets. But when you look up the word judgment, that the root core of judgment is separate, to discern by separating. So it's really this, not that. That's the basic meaning of judgment, is this, not that. So that's a zero or one right there. When you judge, you're making a choice, this or that. right? And I
Yeah.
think so many things come down, like measurement is another one of those things where, and I think in some way that aspect of judgment lines up with measurement, but I haven't really figured that out in my mind.
Okay. Yeah, I think we're going to get there.
Oh,
So
cool.
bear with, bear with me. Because you touched on two different things and they're kind of mushed together. So we'll pull them apart and maybe things will
Okay.
make. Um, so try and maybe jump from where we are, that the mathematicians, they mapped the idea of algorithm onto the world of mathematics as it was. There's this huge machinery of math logic and set theory with tied in all sorts of branches. They turned the machinery loose on the theory of computation. All these crazy things came out of it. But if you get back to the real world of computation, there's something that the hardware guys like me see that the theoretical guys don't see. And that is, if you take the abstract systems and you break them down, okay, I'm going to try and go your direction. You can keep simplifying. You can do a reductionist thing. Well, I can imagine a Turing machine is this, and I can build it up from that. And then you go down to the ones and zeros, the binary, the simple number theory. If as a mathematician, you break it down, and now you can do theorems. Once you get down, there's this basic uniform level where definitions have distinct meanings. That's where you get to start doing proofs and theorems and start building up stuff. So a mathematician's instinct is build everything down to the simplest structures. So I know if I can prove something about a Boolean, system, then I know that result will apply to any number of base, 10, 16. I can apply it to anything else. So mathematicians quit there. But in the real world, and it's something I want to, where I left off of, there's all these structures, computational structures, finite state automata, push down automata, Turing machines. You can stack them. In the real world, they're just blocks. You can start stacking these things together to make more complex hybrid computational systems. That's a very natural thing to do from a hardware point of view. Whereas just philosophize here. For a mathematician, you want to do the opposite. You want to break everything down to simplest terms so that you can study it. The physical side, the hardware guys, we want to mix and match and get an efficient systems for doing things. So a lot of times by combining stuff, we can get a way more efficient computational system to approach a unique problem set than if you tried to turn it all into a Turing machine. You could spend forever going through all the little details. So a lot of what discernment, what you're saying, judgment, in one hand, there's two aspects. It's not, you can break it down to binary, simple, study it. But judgment also means discerning patterns. So is it an elephant or is it a zebra? That's not a, your judgment is discerning patterns
Mm-hmm.
from each other. You're not
Mm-hmm.
making ones and zeros. So in the hardware side, you can think of judgment based on patterns recognition, not as yes, binary ones and zeros if you're doing algorithms. So does that make sense?
Yeah, yeah,
So
absolutely. The discerning patterns is super important.
so that's what distinguishes me as taking the hardware, the physics view of computation versus the math theory of computation view, is that when I go into my world, I can mix and match and hybridize systems. I can think in terms of patterns rather than ones and zeros. Um, um, hang on a second.
Sure.
Yeah.
So where were we at?
talking about the way the physical view of computation can be quite a bit qualitatively different than the mathematical view of computation.
And why does that matter?
Uh, well, it matters if you want to build something. So it's, as an engineer, it's one thing to debate and discuss and wonder about something, but when you have to start building something, you find you start asking completely different questions. All of a sudden, things that were details before to be ignored now become uh, points that a project can live or die on. So um, engineers often take a completely different view of computation rather than the mathematicians, which kind of brings me back to why I was pointing it to Turing and how the world of computation changed from math to engineering during his time at Bletchley Park. So I'm not seeing us. There we are. Okay.
So, I mean, does that, when you originally talked about the world changing on Turing, so that by the end of the war, it was the computation was like more in the field of the engineers than in the field of his way of thought. You made it sound a little nostalgic, as if there might be some reason to go back again to Turing. But now I kind of hear you saying that there are advantages to the engineer side of this. So
there is, but I would say that it's not nostalgic. I think it's useful, important to go back and look at Frege. That
because with Frege, we get all the way back to the language.
We go back to the basics, and because something's going to happen now that we've built the hardware, and you can mix and match, and you can have nested systems, distributed systems. Now all of a sudden, the maths that we've had isn't useful anymore. And this is something I would really love to ask Balazs Kegel. Hopefully I pronounced his, because I think he's been on your conversation. You've had him on. And he's the only person I've followed on X who's prominent in AI research, but is also very interested in embodied intelligence and nested agency. And that's what happens when you actually build a computational system rather than just run it as a program.
Well, this is where it ties up. This is where it ties up with Michael Levin, because that's Levin's whole thing, is that the only way you can truly understand something, even in the human body, is if you can build it some way, then you can get at what's actually happening there. If it's something that you're just going to talk about theoretically, you might as well just be talking about the air.
Mm-hmm. So that's what I'm looking at. Well, I'm really curious is what happens to language models? Language models are one trick ponies. You train them on one thing, and then they generate one thing. But if you start combining computational systems to form nested agency, because I equate physical computation with agency now. What happens to the language? Each computational system by itself had a formal language that it recognized. You put models together now, what kind of a language are you going to end up with? What does language start to look like now? Is it nested? I tend to think threaded. I start to imagine language starting to more like a symphony orchestra. If you listen to a symphony, it's not all the instruments are not all playing the same notes together. Different instruments are playing different themes at the same time. There's a threaded, a weaving, a braiding, so to speak, going on within the music. And I'm wondering if that's what's going to happen to language models, that you'll start to see language models break up into threads.
Well,
And
would this
that's
be
why,
analogous to training each language model? Or like if you have, let's say you have, okay, there'd be two ways to do this. You could take Grok and you could train, I don't know what they call them, APIs or something. You train a Grok on a specific knowledge set. Like I
yeah,
train a Jordan Peterson Grok, and then I train a Ian McGilchrist Grok, and then I train a Paul Vanderklay Grok, or I don't know what that
yeah,
would look like.
yeah, they're talking about that.
Yeah, and then set the three of them talking to each other. That would be one way of doing it. Another way of doing it would be to take GPT-5 and Grok and Claude and have all of them talk to each other about something. So
Yeah,
which way
but
do you mean when you say um, to
it
have
gets,
them threaded?
well, what I've said is that you can't, language models can't prompt themselves. That's one of the problems. But people have reminded me, yes, they can. You can put two language models talking to each other, and they'll go off, and who knows what they'll do. But that's not a productive form of self-prompting. Self-prompting, I use it in the creative sense that the language models is generative, it's generating text, but it doesn't have the ability to stop and go, wait a second, that doesn't make sense. Take that, everything I've said, and throw it out. Let's start over again. Like someone asked Grok, supposedly can answer graduate level physics problems, but yet I've seen personally Grok not be able to answer a question about machine harvesting of tomatoes. It got it wrong with a lot of authority. And if I'd said something answer like that, what would I know about farming? Because I live in a farming community, and I would go, no, wait a second. That doesn't make sense based on my experience. There's something wrong with what I just said. Grok can't self-prompt in that sense that go, no. And if Grok senses a gap, it will make up an excuse. So like,
I do have a funny story to tell about that. Years ago, we had a farm. We lived on a farm in Iowa, and we were very young, like in our early 20s, trying to figure out this whole farming thing. But I mean, there were a lot of things we did understand. We understood how to feed ourselves, how to butcher a chicken, and how to grow vegetables and all that kind of thing. And we made some friends from town, and the wife worked as a kind of like what you would call now a communications person, writing pamphlets, but she was writing pamphlets for the Farm Bureau. But she was not a farm girl. And she had been given the task of writing a pamphlet on how to butcher, the most efficient way to butcher chickens. So she told us, she started reading her pamphlet to us. You take the chickens by the legs and tie them to a clothesline and get them all lined up on the clothesline. And then you can come along with your razor and just chop off their necks. She had no picture in her mind what would happen if you.
no, that's not how I remember seeing it done.
Yes. Well, because what happens if you cut the head off a chicken is it goes crazy. It goes running around the yard and spurting blood everywhere.
Which is a phrase, running around like a chicken with his head cut off.
Except they're all hanging from the clothesline. They're bumping into each other and blood is going everywhere. She was so confident that what she had come up with was the most efficient way. It's just the way Grok gets sometimes, or Claude gets, when they're so certain about something, but they have no understanding of what the actual physical process is like because they're not embodied, right? Or maybe they don't have the experience, or it hasn't been written into their data set what is the best way to butcher a chicken. Or even if you had read what the best way is to butcher a chicken, if you also don't understand what happens to chickens when they get their heads cut off, you're not going to have the whole picture. So yeah, I can fully see that.
Well, my folks came from Sioux City out to California during the war. But when they went back when I was still a kid, and my dad still had family that on the farm that didn't have electricity. and the old pump in the cistern at the
Oh yes,
kitchen sink,
I've lived that way. Yep.
and butchered chickens. I saw it. Yeah. I had some cousins once that we had to pump water for the cattle. And I coming from the city, I thought that was the coolest thing in the world to just be out there jumping. It took my full weight as a kid to get this pump to go. And they
Mhm.
probably thought, wow, somebody doing our work for us. But yeah, the world has changed since I was little.
Yeah. Well, I mean, in some, obviously for the better in some ways, but but also those are invaluable experiences.
Mhm.
Until you know how hard it is to do things, you have no appreciation for the people who came before. And that's what
So,
you're doing here when you're looking back at the history of how we came to even have large language models. It
mhm,
all arises out of this original history going back to somebody like
right.
Frege who did all that work with his models.
So what I'm suggesting to get back is that to try and understand what's happening with nested agency, we need to go back and do what Frege was doing with diagramming sentences again, looking at language as if it's a symphony, playing music, and how, if you listen close, you can pick out an instrument and follow it. And I think that's what Frege was doing, that he was looking at language, listening for the logical progression of how you put a word problem together. And he pulled that out and diagrammed it and formalized it. And that's how we got math logic. I'm thinking we should go back, look at whatever it was he was doing, listening as a linguist, the whole structure of how we use language, how we communicate, and pull out different threads. And I suspect something like Mark Solm's work with multiple consciousness going on, that there's different layers, or the Gilchrist, the right brain, left brain. There's different parts of us are listening to different pieces of a sentence. And that might be an entry point into re-looking at language again. So there's a lot of back and forth now. Our large language models, uh, beginning of general intelligence. Are they intelligent at all? Are they just stochastic parrots? Um, but I think we need to realize language models, as they're currently being implemented, are actually only a fraction of what you could actually do with the technology that these machines are running underneath. So um, I think there's a lot more waiting for us if we go back and try and be Frege again and look at fresh eyes what he was doing. So
Is
again,
that something that you could, is that something you could ask AI to do? Is there a way
I
to
sort of
formulate
I've
the
tried
problem?
questions like that, and I don't get anything useful. Grok just kind of repeats yeah, it's a good idea, it's kind of cool. People have, but I really want somebody to go in and grab it, and, by the collar and shake it. And that's why I'm thinking Balash should be a good person, because I have a suspicion that he's going there already as an AI
Mhm.
theorist, and that's not
Well,
my area of expertise.
so you've listened some to Elon Barinholtz, right?
A little bit. Um,
Do you know what he's getting at when he talks about language being recursively regressive and autogenerative?
a little bit, I
And
think.
then he says that he believes that LLMs are that way too, and that therefore our language system is the same as the language system of an LLM or something like that. I might not have all the details right.
I'm not. My opinions are varied yet. I've tried to listen to some of his stuff. He says things that really resonate, and then he says
Mhm.
things that leave me confused.
Yeah.
Uh,
I feel
He's
the same way.
using,
I mean, there's things he says that I'm like, yeah, I'd really like to talk to him about that. And then, but I don't exactly understand what he means about auto-generative.
he's using definitions in his own way.
Okay.
I, if I had to put my finger on it, that's where I would try and start and go, okay, if I'm a bit confused, maybe he's using these words in a different sense than I'm thinking of them. So I need to go back and take a deeper dive to see what he's thinking about when he says what he says. Um, my gut sense is that yes, he's onto something. I'm not articulating it clearly enough yet.
Well,
So
I guess one of the things that comes to me when I'm listening to him is something that I've thought about a lot, just from a layman's perspective. There are some people who believe that language started out with a word here and a word there, and that eventually it built into a grammar, and then eventually that grammar built into a structure. But when he talks about language being recursively regressive and auto-generative, it almost sounds to me as though he's saying what I believe is that the structure was first. The structure was fundamental, and there was enough language in the structure to communicate effectively right from the get-go. And then obviously the number and variety and diversity of words and languages has grown since then. But what do you think about that?
ah, yeah, there's some ore in that vein. Let's just put it that way. That language began, animals have language.
Mm-hmm.
So, but that's clearly not what he's referring to. Any social group, any has a language. If you want to just go back to but if you remember Chomsky's hierarchy of languages,
Mm-hmm.
different language classes correlate to different computational systems. So you can map consciousness levels, of an animal based on the computational system necessary to reproduce its environment, its language. That's kind of a fuzzy thing, but we as humans, we're the pinnacle of agency on this planet. So we're not necessarily a good benchmark to judge language for all the other living systems on the earth. Like I've pointed out before, Mother Nature doesn't see the universe through our eyes. So we need to sometimes put ourselves on the back burner and try and see Mother Nature through her eyes. So when nature is looking at animals, a wolf pack or chimpanzees or ants, their reality is not ours. So language at that level is something different. But they have a language nonetheless, if you want to think of it in terms of the mathematical definitions. Now, for the ants, they have a dance, they have pheromones, scents, and stuff. They communicate to each other, and then they keep going. So
Well,
the fact that
I was thinking about the dance that the bees do. A bee will do
yeah,
a dance to explain how far away the field is, where the honey is, and how to get there, and it's all communicated in that dance. But if we
right,
step back one step and think about it, then the bee needs a language, because if they didn't have a language, they wouldn't survive as a hive, because they have their scouts. Well, first of all, they have scouts, but the scouts
yeah,
go out, and then they come back, and they have to have some way to communicate what they have discovered. So that structure has to be there for the hive to survive at all. If the hive
yeah,
doesn't survive, it doesn't reproduce. So that structure had to be there in the beginning.
Yep. Yeah. But now we're back to, is math invented or discovered?
Yeah.
And you come back to, yes, math is discovered. The patterns that we call math are already out there in some physical sense.
Well, but I mean, in terms of human language being different than an LLM, that structure is so deeply embedded in us as human beings that we don't really even have to think while we're talking. You could start talking and just go on autopilot and just blah, 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 blah. Really.
And some people do.
And I do sometimes. Okay. But with an LLM, they're somebody said something like they're a plagiarism engine. I mean, they're just scooping up language that's out there, that's available, and putting it together with this probability filter in amazing ways, absolutely amazing ways, the way it can bring all this stuff into something that's always very usefully organized with bullet points and 50 pages of text for a simple question.
Some of our fellow human beings are exactly that. Mm-hmm. And so, yeah, as a student, I encountered 3 different classmates over the years that would have what you would call a photographic memory, the ability to look at a proof once, 6 months later, go up to the board and write it down, the papers and stuff. 2 of these fellow classmates, I worked with them. They were brilliant. They're absolutely, another level above me. And when you combine that with a photographic memory, you're unstoppable. But one fellow student was like this. He was consistently the high score on exams, homework, But if I tried to ask him a problem to solve, he couldn't do it. And somewhere along the way, after a year or so of being fellow classmates, it dawned on me he was just memorizing all the solutions out of all of the textbooks. So ever since then, every time I see someone who's supposedly really smart, that part of me goes, okay, is he just repeating stuff? He has a good memory, or do they really know what they're talking about? And some people I've decided are just really good LLMs. And we treat them as being
I
brilliant.
think that gets at the core problem with our educational system, because I notice this with a lot of younger people that they feel more comfortable memorizing the process and memorizing the answers than they do trying to understand what's underneath. And that mostly that I saw with the educational system, tutors and so forth, they don't really help you understand why something is. Mm-hmm. It's just that. Yeah. This is it, memorize this, calculate, get on with it. And my husband was always trying to say to these young people, look, you have to understand why calculus is the way it is in order to be able to really appreciate it and use it in a way that's flexible and, productive. No, we're just going to learn the formula. And there's only so far you can go if you just learn the formulas and you don't understand the underlying fundamentals of a thing. And I mean, maybe I think probably the LLMs know the fundamentals of a thing because all that data is out there, but maybe that is knowing it and grasping it at an embodied level are probably 2 different things.
I think so. Well, pull everything back. I think a lot of what we do is the same as what an LLM does. So they're not but we have the ability to self-prompt, to jump out, to switch gears, to go, oh no. That's the distinction. A lot of when we're talking, we are on autopilot. We are auto-generating text. But that's partly to help us communicate. What the language models can't do is switch gears. If we give them that ability, then they will be a lot more scarily awesome. So Balash was talking about, he called it a perplexity index. And he hasn't said anything more about it. It's a measure of how surprising the next word is that the language model will produce. So if, hopefully I get this right, if the index is 1, that means the next word that comes out of the LLM is perfectly predictable. Now, if you look at human speech, okay, I'm just going to throw a number out. Our perplexity index is maybe like 10 or 5 or 10. The more surprising the next word is, the more information it carries.
Mm-hmm.
But if the next word is too wide open, then it makes it hard to communicate.
Mm-hmm.
So there's a sweet spot in conversation or in language, in perplexity, where it's surprising enough to communicate information, but it's not so surprising that we have to stop and think about what we're listening to try and figure out what's being communicated to us.
Yeah. Yeah.
So the large language models, if you just let them do their thing, they would have a perplexity index close to 1. If you ask Grok the same question, it would give you the same answer. So to make it sound more like human speech, the language models have a little bit of fudge, randomness thrown into them to make it so that be slightly different answers each time you ask it the same question. But so yeah, I think if you're comparing language models just to repeating stuff, a lot of what we do is going to be that way because we don't want our perplexity index of our communications to get too high. So we're going to listening to Morse code. If you first do it, your dits and das, you kind of like and then after a certain point, your brain switches gears and you hear combinations of dits and das. So you hear letters, and then at some point further, your brain makes another switch, and you start hearing whole words, and you start recognizing text streams in Morse code because you know what's coming next now. And so there's a place where perplexity plays into being able to understand Morse code. So the old timers could go, 40, 50 words per minute Morse code, which is about half as fast as you can talk.
Mm-hmm.
So these old timers could almost have a conversation in Morse code, but you can do that because your brain knows what mostly is coming next. So it doesn't have to pick up the individual dits and das or letters. It just, post. You pick out words, but you could narrow down what the word is coming next. So it makes it easier to decipher or decode that next word. So,
well, that's why it's possible to compress data without too much loss.
right, there are compression algorithms which are better than Shannon because they take advantage of the fact that your brain will fill in missing information.
Mm-hmm.
So that's kind of interesting. Just for trivia, there are audiobooks in Morse code if you want.
Wow. Who knew?
Yeah.
Well, I think one of the other ways that you get a perplexity index with human speech, at least I notice this happening with myself, is a lot of times there's a word right on the tip of my brain that is going to fill a slot that I know is exactly the right word to communicate what I need to communicate, but that word's just not, that tumbler's not tripping. Mm-hmm. So I have to find another way to say the same thing. Either I have to find another word that's peripheral, but not exactly, or I have to build another phrase into the sentence that includes all the meaning of that particular word in order to fill the gap, in order to communicate. Mm-hmm. And so you get this automatic built-in perplexity index just because we're not perfect to always have the exact word at our disposal at every moment. Mm-hmm. And then that's always making our language shift and change, very much like a a musician might decide to put a little bit more vibrato into a tone or something, and that's going to change the whole tonal quality of the themes playing against each other in the symphony.
So poetry will have a high perplexity index because it makes you want to stop and think and get pulled into the words. Whereas if you're out in the field in a military situation, or construction site, or logging, or some occupation, communication has to be clear and to the point, because somebody's life might depend on it. There, the perplexity index has to go down. So, when you start to criticize or think about language models, you have to remember that's at play with us as humans in communication as well.
Yeah. Lots to think about. Well, I'm hopeful that I can get you and Balazs together so you can talk about this.
I don't know if he wants to talk about it. He put it in a preprint, and I saw the preprint, but he hasn't said anything more about it. Because I was kind of excited about what he was proposing.
Well, he talked about it at some length the last time I had a conversation with him. Because I do remember him talking about the perplexity index when he was explaining to me exactly how the LLMs work. But this is probably a good point to stop here. I think we accomplished most of what we wanted to accomplish. And what we have discovered through this conversation is that if we want to make some leaps forward, it might be good to look backwards at Frege and find a new way of applying his approach to kind of graphing out what language is actually doing.
So you were talking about the binary. I haven't gotten to finish that up yet, but there's the mathematical reduction, everything down to binary ones and zeros, because then math and logic become equivalent. It gives you a powerful math tool to prove theorems and stuff. But physical computation, you can work in patterns. You don't have to work in binary. But if you're running an algorithm, at some point you have to make choices. In physical computation, or what you call agency. Agency is about making choices. And in the real physical world, a choice is binary. You either make it or you don't make it. So there's that sense to the binary, yes and no, is the physical act of making a choice, which is an irreversible action on the physical universe. So choice changes the physical universe forever. And that's the no thing versus the binary, which is the mathematical game. Does that help make sense?
Yes, very much. And that brings us back around to where we ended last time, which was on this idea of physical computation acting back upon the physical world. which obviously can happen in any number of ways, which we don't have time to go over right here, but people can use their imaginations. Robots, there's robotics, and there are even, last time we talked, we were exploring all of the different kinds of physical computation that aren't computers, like, for example, card games or square dance, symphonies, things like that. And that is definitely a kind of physical computation that acts back upon the physical world, and in many ways can even act back upon the emotional world and the cultural world.
Yep.
Right.
Yeah. And so one last working example, because I'm not sure if we'll have another conversation on this. One way to think that I think about nested computation is, imagine a game of checkers. that has two players, and that's a game of rules, sequence of choices defined by a set of rules, win or loss functions and everything. Now, imagine you added a second set of players that take over the board. The first two players play by the rules of checkers. They move pieces. The next, at some point, they break. The second set of players, they play patterns. They don't move pieces, but they look at the patterns of the checker pieces, and they get to move whole patterns. And then that goes for, say, they're done, they let go. Now the original two players now play pieces again, and then it shifts off. And now, so when we're talking about languages being a sequence of symbols, well, for the first two players, the language is pieces and moves on the players. The second one, the symbols are patterns, and the movements are patterns. So think about language models now. We manipulate words and sentences, but a language model can manipulate patterns. It's the same mechanism. So there's language models in a sense that generate music now based on patterns. There's language models that generate graphics and animation now based on patterns. So when we talk about a computational system, it doesn't have to be words. It can be all sorts of things.
Well, that makes me think about a couple of different things that happen aside from computation. I've been part of different projects where maybe a half a dozen artists decide to get together and do a painting. Mm-hmm. So one artist will start the painting, and then they send it in the mail to the next artist, and the next artist adds their part, and then nobody knows exactly what the painting is supposed to be. It's just somebody started something, and then now you're going to do something based on that something. And it goes through until the sixth iteration when the final artist has the mm-hmm. responsibility of bringing it all together and making it something. Yeah. Okay. Another thing I've been a part of is telling a story with a half a dozen other people, where one person starts the story and the next person has to look at what's there and add on to it. And you keep going, and then you have to come up with a story based on that, right?
Yeah.
That is something that large language models, if we set them tasks like that, where each one is being the prompt for the next one, but then they have to navigate that creatively to figure out what the pattern is and how that pattern might be instantiated in a progression.
Yeah, you remind me, my first year when I was living in the dorms, this is like 69, there was a bunch of guys in the dorms that would take over one of the conference areas that had blackboards on all the walls. And this is before Dungeons and Dragons. And they would have this game where they would start telling a story by putting pictures on the board, and then add a story, and then somebody else would add, and the story and the boards would just kept growing until, after a day of playing this game with each other, they'd fill up this whole room with the story. And I was thinking, that's exactly what language models can do if mm-hmm. they're given the right tool or switch or whatever it is to get there. Mm-hmm. So yeah.
Well, we're on the same page.
Yep.
Which is nothing short of miraculous. But this has been really fun, Glenn. Thank you so much for joining.
Okay.
And
thank you.
And we'll stay in touch. And okay. I hope I can get you and Balazs together one of these days. So
someday, yeah, we were going to do it, and then I had my little ER visit, and life went a different direction. But yeah, it would be fun to try it again.
So glad you're doing better. Have a wonderful week, and we'll talk.
Okay, thank you. Take care. Bye now.